Hello and welcome to What's New in Aerospace, sponsored by Boeing. Thank you for joining us here at the National Air and Space Museum in Washington, D.C. in our gallery Moving Beyond Earth. I'm Matthew Schindel. I'm the curator of Planetary Science here at the museum. And with me today are Dr. Jim Green, the director of NASA's Planetary Science Division, and also Dr. Thomas Waters, senior scientist from the museum's Center for Earth and Planetary Studies. And our topic today is the moon, and it's inspired by a new exhibition here in the museum called A New Moon Rises that features the camera system from the Lunar Reconnaissance Orbiter and some incredible photos or images that show you the moon probably as you've never seen it before. Tom is going to show us some great images, but before we get to him, I just wanted to show you one of my favorite images. It features some lunar swirls that are found on the lunar surface, features that are still somewhat mysterious to scientists, and you can see a couple of examples of those here in the gallery. So our format today is we're going to do something sort of conversational with our speakers giving sort of brief presentations, but with the audience able to ask questions before and in between those presentations. And I'm also going to try and get our guests to sort of talk with you and talk with each other by asking them some questions. So I'll start off with the first question to Dr. Green. So Dr. Green, can you tell us, why is the moon scientifically interesting? Why are we still going to the moon?
Well, the moon is our closest planetary object. We've looked out for millions of years and wondered about the moon, its origin, and what it's made of. Is it made of green cheese or not? Well, we know it's not, and we know it's made of Earth material because its early origin, we believe now, occurred more than 4 billion years ago when a planet the size of Mars impacted the Earth, creating the moon and the Earth. So they're intimately tied in the materials they have. And so in fact, if we want to know the origin of the Earth, when that occurred, we actually can only find that answer by going to the moon.
All right. And let me remind you, anytime anyone from the audience has a question, just come up to the microphone, and we do have a special incentive for you today. You can have a NASA lapel pin if you get up and ask a question. All right, while we wait for someone to come to the microphone, okay, go on up to the microphone.
So about the moon, I was always wondering when I heard this story that Earth has been created in two things. I was wondering what would have happened if there was no meteorite, no little asteroid hitting. So how would the Earth today, as we know it, would look like? Bigger gravity, bigger. So how can? Because it's by any it's just chance that it looks like it is today.
Great question. So how would the Earth today be different if that Mars-sized early protoplanet hadn't collided with it and created the moon?
Well, one thing is we may not have life as we know it.
Yeah.
We now believe life started in the ocean. And the moon, of course, produces tides back and forth. And for life in the ocean to move to the land, the tides may have contributed to that. In addition to that, the moon provides an enormous stabilizing force in terms of our rotation. It allows our axis to spin like a top rather than do a topsy-turvy thing, which then would change significantly our climate all over the land and perhaps also inhibit life as we know it today. So the moon provides a lot of important features that we want to know more about and its role in life.
No, it's a great question. If you look at the moon too, and you'll see this, one of the amazing features of the moon is pretty much it records everything that hit it beyond a certain point in time. And some of these are really large basins. I mean, these are 1,000 kilometers across in some cases. So we're talking about very, very big objects that hit the moon. Well, think about what would happen if the moon hadn't been there. Some of these objects may have impacted on the Earth, which at times could have also affected the development of life on this planet.
All right. Great. Well, let's take one more question from the audience, and then we'll get to our first presentation.
So I was looking at the picture. What are the lunar swirls?
Tom, do you want to try and answer that? What are the lunar
It's a great
swirls?
question. They're actually really very mysterious features on the moon. It's almost as if you took the lunar surface and got a spray can and just sprayed a very light coat of material on the surface, because that's all it is. It's a very subtle difference in the brightness of the material. And we think it's because when the moon, which has no atmosphere, is exposed to solar wind and cosmic rays, it affects the surface. Fresh material that's created when an impact occurs will be lighter, but over time it darkens, and that darkening happens because of this interaction with the solar wind and cosmic ray particles. And what we think may be going on is that there are certain areas of the moon that are protected by the moon's magnetic field. It doesn't have an active magnetic field now, but it did at one time, and it's preserved in some of the rock. So it's this remnant field, and that may be shielding or interacting with that solar wind to kind of help protect certain areas of the soil from darkening as rapidly as other areas that do not have that kind of shielding. That's just one idea.
All right, great. Well, on that note, why don't we turn things over to Dr. Jim Green to tell us a little bit about the Lunar Reconnaissance Orbiter.
Thank you very much, Matt. All right, what I'd like to talk about today, if I can have my first slide, is indeed a little background on the Lunar Reconnaissance Orbiter and why it came about and what it's currently doing. All right. So as we talked about earlier, why do we study the moon? Well, the moon may indeed be extremely important to us, as we say, not only in participating in some way about harboring life here on Earth and how life as we know it has evolved that way, but it also shows that we've been on the moon. Here's our Apollo astronaut on the moon. And so there are 5 basic things I'd like everyone to know about the moon. The first one is our astronauts on the moon have actually brought back lunar material. We have more than 800 pounds of lunar rocks and regolith, which is the soil on the moon. And we're currently analyzing that. And that has been going on for more than 40 years. And it constantly surprises us in new and in very important ways. In addition to that, on the surface is 6 landing spots. So we've had humans down on the ground working and deploying instruments in addition to bringing back soils and material. These are the Apollo sites. The second thing, as Tom mentioned, the moon's surface really records what we call the bombardment history of the inner part of the solar system. When we look at the moon, it's full of these craters, but the Earth doesn't have craters like that, not today. So what's happened? What's happened on the moon is without an atmosphere, those craters remain relatively pristine. Here on Earth, our biosphere has literally destroyed any hint of those kind of craters, although we do see hints of crater-like features in various places, but they're very few in number. And so understanding that bombardment history is really important to understanding how the Earth has evolved also. Now, in addition to that, we now know that the moon actually has some of the coldest places in the solar system. You know, the light from the sun that shines on the moon illuminates it everywhere, we would think, except when you look at the poles. There are certain craters that are so deep that indeed the light, even over a lunar day, doesn't get into the deep part of the crater. And so it is some of the coldest places in our solar system. And then finally, with the Lunar Reconnaissance Orbiter, we're really looking at the moon like we've never done before. And so here are the 6 landing sites. They're all on the front side of the moon. And this image, these 2 images, are not only the front side of the moon on the left, but the back side of the moon on the right, all from the Lunar Reconnaissance Orbiter in huge detail. And we can examine those and understand those much better. So what about LRO? Well, LRO was designed to study the moon in great detail. It was really our next step, not only scientifically, but providing us an opportunity, if we need to, for humans to go back to the moon. It certainly provides us with high-resolution imaging, the opportunity for our rovers and our landers that many nations are now sending to the moon to be able to be set down safely on its surface. Now, the goal of the Lunar Reconnaissance Orbiter was really to do that high-resolution imaging, to create a new atlas of the moon at very high resolution. And in fact, if you look at that control stand over there, if that was sitting on the moon, you could easily see it with the Lunar Reconnaissance Orbiter. This stage would be many pixels and easily picked out. And so, now we've got maps like that through the entire surface of the moon. We also want to look at it in different ways, like its temperature distribution. We also want to search for resources like potentially water, particularly if humans go back to the moon and want to be able to create colonies or work in that environment. The Lunar Reconnaissance Orbiter was launched in 2009, and after a few months traveling and getting into orbit around the moon and then commissioning the instruments, it then really began to do its work. So here's a picture of Lunar Reconnaissance Orbiter, and it's got 7 instruments. The first one's Crater. This one looks at really high-energy cosmic rays that bombard the moon. Diviner, this one maps the moon in temperature. Temperature here on the Earth is very different, also on the moon. Lola is a laser altimeter. It tells us the highs and lows. And LROC is that high-resolution imager that allows us to make detailed measurements of the craters. LAMP allows us to look for water vapor trapped in these permanently shadowed craters. And LIN looks at the neutrons that come from underneath the surface that tells us about water. And finally, the Mini-RF is a synthetic aperture radar that examines the soils, looks at the regolith, its distribution. Here's LRO, and it's a huge spacecraft. How big? If LRO sat here in this exhibit, it would be about the size of this shuttle mock-up as you see it right here. So very large. Also, LRO is taking images like this. Here's where we've combined the Lola images that are these colored images of highs and lows, blue being low, with the LROC images. Here's a basin, meaning an impact region which was absolutely enormous. Here's also the Tycho crater in great exquisite detail. And sitting on top of this mountain is a house-sized rock. Now, Aristarchus is a plateau region that's very different than what we've seen elsewhere in the moon. And of course, here's evidence of our landing sites. Here's Apollo 17. You can see where we've launched from the lander. You can see the rover, and you can see the tracks that have been made by the astronauts that have transited across the moon. So, LRO is in orbit today, working in a spectacular manner, making detailed observations, and continuing on doing its mapping. So with that, I'll turn it back over to Matt.
All right, thanks. And remember, if the audience has any questions, please step up to the microphone. Again, there is an incentive. If you ask a question, you get a lapel pin. Well, it looks like we have someone with a question right away.
How long is it going to stay in orbit around the moon? I know that eventually orbits decay, right? So how long have you guys planned for its mission to go on for?
So LRO has an enormous amount of fuel. In fact, more than half of it is fuel. And that has served it well. It allows it to adjust its orbit over and over, and it turns out it absolutely has to do that. You know, the moon actually is very irregular in terms of how it attracts spacecraft. It has different mass densities. And so those orbits constantly decay. It has enough fuel to last at least for another 4 or 5 years.
All right. We have another person stepping up to the mic, but let me ask you a question before they do. Those images of the Apollo lunar landing sites are really pretty incredible, that even today you can see where the astronauts walked and roved.
And in fact, if you look closely enough, right where the lunar limb stand is, you can see the backpacks. So when they walked up the ladder and they threw their backpacks off and entered the capsule, there they are. The two backpacks are laying on the ground.
So if we do send another mission, do you think NASA could bring back one of those LEMs for the museum?
Well, that's a good question. Actually, we discussed this a little bit in the sense of these are historic sites. Should we really go back and tamper with them or not? So I would say the story's not in on that one.
Okay. Well, maybe we could just send a curator up there. That would probably be good.
We may have to.
Hi, my name is Fahad, and being here was a complete coincidence. Actually, my research area back at the University of Tennessee is with Dr. Lawrence Townsend. We're using Crater actually to find water on the moon. Being here was a complete coincidence. I don't know about that. Anyways, the images from LRO have helped us to find stuff that was lost on the moon. Some of those are the Soviet landers or rovers, for example. Every time in the news we list like we have a new thing found on the moon. I'm just wondering, are there stuff that are still lost on the moon that we haven't found them yet?
Yeah,
and are to be found using?
Yeah, that's a good question. So what you're referring to is the Soviet Union also launched missions to the moon with rovers. And one rover in particular, after quite a while roving, actually they didn't really know exactly where it was. And it really took LRO to find it. I think we're in pretty safe grounds to say that's probably one of the last things that humans have made that's there that was lost that we found.
Are there any more that we are looking for?
No, I don't think there's any more that we're looking for, but you can always scour the image and let me know if you find something.
Thank you very much.
In fact, there is an image in the exhibit upstairs of one of the lunicods. So you can actually see that on the...
Mark Goldberg. If we do find resources on the moon, if things are found that are valuable, what are the implications of exploiting those resources?
That's a good question. And of course, you're talking to a planetary scientist, and the first thing I'm going to say is, we don't know enough about the moon yet to be able to say it's up for grabs. I mean, we would much rather study it, understand it much more closely, really do the analysis of what's there, how did it get there, what its evolution is, before we let planetary resources tear it up. Because it provides us valuable information, valuable science information.
Is there a legal basis to prevent the exploitation of resources?
That's another good question. You know, there has been some laws passed now that allow entrepreneurs to be able to go out and mine asteroids, and I believe the moon would be probably considered fair game.
All right, do we have time for another question before we move on? Yes? Okay, great.
I'm Sabor Schweiner, and I'm wondering if these LRO data will be publicly available, so can I access them through internet?
Yeah, the LRO data, all of it, and the high-resolution images are all available on the web. So it's very easy to be able to go and do one of your favorite search engines and go LROC observations and go to a site at WashU in St. Louis where they're archiving and putting online the LROC data.
Yep.
Rob Thomas, and I'm interested to know what we're still discovering from some of the material that we brought back 40 years ago. If the imagery that you're using now and that information cross paths in an important way.
Yeah, one of the most startling things that we discovered when we brought the lunar material back was their ages. You know, as I mentioned, the Earth has turned over and over our biosphere, our plate tectonics, and has created new material in a constant way. You can't go anywhere on the Earth and find a rock 4 billion years old, and yet the Earth is even older than that. But you can on the moon. And so when we brought material back and we started to age date it, we found We did indeed find the old rock, the 4.5 billion year old rocks that were created when the Earth and Moon system came into being. But we also found a whole series of younger rocks, those in the age range of about 3.8 billion years. And we were very puzzled by that, but we now believe we understand that more. What happened at 3.8 billion years was an entirely new swarm of material coming from the outer reaches of our solar system, bombarding the moon, the Earth, Mars, and all the way into Venus and Mercury. And that is called the late heavy bombardment. With that, we also believe it brought a significant amount of water. And so the discussion right now in the planetary fields are how much water was brought to Earth based on those events than was here on Earth. And the answer might be as high as 60% or as low as 10%. And of course, water is critical for our life to exist here on Earth. So there's a lot of clues like that that we're uncovering now that's just really fascinating.
Great. Well, on that note, we're going to, oh, sorry. We have an online question. What emission filters are used for the LROC? Exposure times, correcting for any movement artifacts? Tom, you might be the best to answer that.
Okay, well, in fact, which I'll talk about here in a minute, there are multiple cameras. The wide-angle camera does have filters. Those filters are, in fact, designed to look at the visible spectrum. They kind of sample it so we can get information about the color properties of the lunar materials. The exposure time really varies depending on what the solar illumination conditions are at the time. I hope that answered the question.
All right. Okay, one more question.
Hi. I would like to ask, when you mentioned that the moon have one of the coldest places on the moon, those big holes, I suppose as low as you go, the coldest it is. How low have you gone so far? And I suppose if you go as low, as deep as possible, you might find ice, which means it's water.
Actually, oh, that's a great question. I love it. And the reason why is we want to go into these permanently shadowed craters. Because the bombardment history of the moon is not just with rocky material. We believe comets also hit the environment, not only at Earth, but also on the moon. And when that occurs, that water, one of those volatiles we call it, ends up migrating and ends up in cold traps, which are in these permanently shadowed craters. So if we want to know what the early solar system cometary material looked like, it may be sitting in the permanently shadowed crater on the moon. Let's go get it.
How low have you got into one of those?
So there's a couple ways that we look into this permanently shadowed region. We can't see it with LROC. Now that's very hard to do because the sunlight doesn't shine there. But with the LOLA instrument, which is a laser altimeter that fires laser beams down to the surface, reflects that, and has it come back up, then we can make that time delay measurement, tells us how deep they are. Now they're the normal deep craters. And craters have a variety of depth from meters to kilometers in size, and they're all over the place in terms of their depth. But they're the normal craters. They just are in an unusually important place, North and South Pole, where the sun don't shine.
All right, now we're going to move on to Dr. Thomas Waters from the Center for Earth and Planetary Studies here at the museum. And Tom is going to talk to us about some of the surprising discoveries that LROC has made, and also give us more of a tour of the LROC exhibit, A New Moon Rises, and the LROC itself.
Yes, which I really, for those of you that are here, I really do invite you to go up onto the second floor and visit the new gallery. We have over 60 prints of various landscapes on the moon, which is, again, one of the things that we did this exhibit for was really, we want to teach you something about the moon, but we really want you to walk in there and just be surprised by the beauty of the landscapes of the moon, because you don't really get to see those just looking at up at the moon, at the sky, even with a telescope. you really need this perspective from the spacecraft that LRO has given us. And that's one of the great things about the Lunar Reconnaissance Orbiter Camera. It has really allowed us to see the moon in ways that we just never were able to see it before. And it's a real team effort, and I'll move to my next slide here, but I'll talk a little bit about the cameras. We talk about LROC as a camera, but it's actually 3 cameras. There's actually 2 telescopic cameras on board, and these are literally, as I said, they're telescopes. They're taking very, very high resolution images of the moon. As Jim was saying, they can resolve features that are on the scale of some of the smaller objects in this gallery. I mean, we literally can image the surface at less than, or at around 30 centimeters in some cases, which is 1.5 feet. Again, it's amazing. These are the pixel scales we're talking about. We also have the wide-angle camera, and the wide-angle camera, as I mentioned before, has a series of filters where we can sample the visible spectrum and part of the UV spectrum, and that's to help us understand the chemical nuances of the materials on the moon. I just want to point out again that there's an enormous effort that goes into bringing these images back, and the ones that we have in the gallery. I mean, I can't emphasize enough, we're talking about hundreds of engineers, technicians, scientists that are involved in the design, building, testing of all these cameras before they're ever flown. And this is a picture here of the narrow-angle cameras, the telescopic cameras, the 2 of them, and the wide-angle camera being tested at the Malin Space Science Systems facility where these cameras were built. In addition to that, again, there's a team of people led by Dr. Mark Robinson at the Arizona State University. Mark is the principal investigator of the LROC camera. I have the great honor of being part of his team, and his team consists of many, many people, again, scientists, technicians, all of which work very hard to bring you the images that I'm going to show you and that are also shown in the gallery. So here's one of the remarkable things about LRO and LROC in general. We are literally sending or receiving 440 gigabits of image data a day. That's about 60 gigabytes of data a day coming back from the moon. Right now, the narrow-angle camera, those two cameras have returned well over 1 million images of the surface of the moon. It's just an incredible data set. In fact, if you give us enough time, and I say this to Jim Green because he has to approve our extended mission at some point, if we stay in orbit long enough, and somebody asked that question about how long LRO can stay in orbit, in fact, we can stay in orbit, as Jim was saying, for a very, very long time. If we're in orbit long enough, we will be able to map the entire surface of the moon at 0.5 meter to 2 meters per pixel. It will be an incredible data set. We're already well on our way to it. And then the wide-angle camera also produces a more synoptic view of the moon and gives us these great, again, global views that we can then, again, image the moon with different lighting geometries, which, again, if you go to the gallery, you will see. And this is just an example of again, Jim showed this of one of the landing sites. This is Apollo 11, and you can see the detail on the surface of where the astronauts actually walked. Okay, so what are some of the big surprises? Because here we've got this wonderful spacecraft. We've got these great telescopic cameras that are imaging the moon at resolutions never before possible. So really, what were some of the things that really surprised us? Well, again, just looking at these images, you can see, again, we were talking about craters. There are craters of every size, from very, very small, craters, again, smaller than the size of this podium, to craters that are hundreds to thousands of kilometers across. So the moon really has preserved this incredible record of impacts. So one of the questions is, are there impacts going on the moon today? And what we do to really answer that question is to look at these very high resolution images. We know, in fact, from Earth-based observations, there have been flashes, literally flashes, that we have tried to, and we assume are connected to the formation of a new impact crater. But we didn't really have the means to really determine how many of those and how big they were until LROC. This is just an example, yes, and the answer to the question is yes, the moon is still being bombarded. It is still being hit by some reasonable size objects. Again, here's just an example of an impact crater that literally was formed between the time LRO got into orbit and now. This is a before and after picture. So it's just amazing, and this is not a small impact feature. I mean, again, you can see the scale bar there. This impact crater is probably 15 to 20 meters across. I mean, it's a fairly good size object, a fairly good size impact crater. In fact, we have found more than 200 new impact craters on the moon, just, again, from the time we got into orbit and now. And those are ranging in size from as much as 1.5 meters to 40 meters. I mean, again, think of that. That's almost the size of half the size of a football field in diameter. So it's really helping us to really understand what that rate of new impacts are on the moon. Much better than we were ever able to determine it before. Well, what about other kinds of geologic activity? Volcanic activity is always a good one. Well, the moon was very, very active volcanically early in its history. All those dark areas, you see the big dark areas on the near side of the moon that you see, again, when you look up at the moon, those dark areas are dark because they're filled with lava. That literally, lava flows flowed in and filled these very, very large basins. And that happened billions of years ago. But the real question is that where it ended? And the answer is no, it did not end there. We thought it did. Up until LRO got into orbit, we were pretty sure that the last major volcanic activity on the moon happened well over 1 billion years ago. Now we've found all these small patches of smooth volcanic flows that fill these sort of low-lying young areas, and they appear to be very young. And the reason they appear to be very young is if when you look at them, you see very, very few impact craters on them. And that's the indicator. If they've got very few impact craters, they're not very old. And in fact, because of that lack of superimposed impact craters, it really suggests that these young volcanic features are less than 100 million years old. Now that sounds like, gee, what are you talking about, 100 million years old? In geologic terms, that's really young. In fact, it's so young that it wouldn't be at all impossible for volcanic activity to occur on the moon today. Okay, here's my favorite. Is the moon shrinking? Okay, so why would we think the moon is shrinking at all? Well, before LRO and LROC, these fantastic images, we knew there were evidence of contraction on the moon, things where the moon was getting squeezed together locally. And this was all coming from evidence from these kind of ridges, these what we call wrinkle ridges. And they're literally formed as the volcanic material that flooded those big basins gets squeezed and pushed into ridges. But they're really pretty old. They probably formed billions of years ago, not long after and maybe even while these volcanic plains, these volcanic flows were filling the basins. So we knew there was that evidence of contraction, but what was really a surprise to me was the discovery of these very small scarps, these features that are literally being formed because the crust of the moon is being squeezed together and it breaks and it literally gets pushed, one part of the crust gets pushed up over the other, forming this fault scarp. And in fact, we've now found thousands of these faults all over the moon that really are telling us that the moon has to be shrinking. In fact, again, these faults, these scarps are so young that it's really very, very likely that they are actively forming on the moon today. Okay, so lastly, so the moon's shrinking. Why is the moon shrinking? What's going on? Well, it turns out that the interior of the moon is still hot. The moon's outer liquid core is still, as I said, liquid. So it's cooling down. As it cools down, it contracts and shrinks, and then the whole moon has to adjust to that. So it's shrinking, that cooling is causing it to shrink. But the other thing that we found out by looking at these thousands of faults is that there's something else helping it to shrink. And that turns out to be Earth. Earth's tidal forces are actually working and stressing the moon in such a way that they are contributing to the shrinking of the moon. And it's just another example of, again, how intimate that relationship between the Earth and the moon is, that even today, billions of years after the moon has formed, the Earth is still helping to shape the moon. Now stop there.
All right, thank you, Tom. And as before, we are open for questions from the audience. If you want to step up to the mic, if you have a question. I'll start by throwing out the first question. So what is the end game of a shrinking moon? Where are we headed with that?
Well, yeah, that's a great question. If the moon is in fact shrinking, and we have this evidence from these thousands of small faults, but they are small faults. That's the good news. So the amount of shrinking that the moon is doing is actually relatively small. You don't have to worry that the moon is going to shrink away and disappear. That will not happen. But it is probably going to continue to shrink as long as that interior is hot and you have the tidal forces working with that cooling.
Only in Despicable Me did it really get small.
Yes. Yes. That's the extreme of the shrinking moon.
All right. Okay, we have an online question. What geological processes powered volcanic activity on the moon?
That's a great question. It is pretty much the same process that creates volcanic activity on the Earth, and that is heating from the interior. The interior is heated enough that the interior rock begins to melt, and that melting expands the material, and it wants to reach the surface. It wants to get out from the interior of the body. So that's what really drives it. It's the internal heat of the moon, both in the past, which was also helped by the fact that the moon was hit in the ancient volcanic activity on the moon, was helped by the fact that it was hit by these very, very, very big asteroidal-sized objects that also help to heat the crust and create volcanic activity.
Okay. All right, we have a few questions from the audience now.
All right, so by far, how many miles of the moon has LROC taken pictures of?
How much of
How much of the moon has LROC taken
Oh, okay.
pictures of?
That's a great question. The wide-angle camera has imaged the entire moon, except for the permanently shadowed areas that Jim was referring to, which we can't really see easily. But the wide-angle camera literally produces a global view of the moon every month. Now, the narrow-angle camera, the telescopic cameras, they take almost, it looks like a postage stamp on the moon. It's a very, very small area because you're taking very, very high-resolution images. Those take a long time. We're probably right now at about 70% of the surface of the moon that has been imaged with the narrow-angle camera. So we've got a ways to go.
Yeah, the moon's a big place.
Yes.
So imagine it being in orbit for 6 or more years. and still we have 30% of it to look at the high resolution.
If the moon is shrinking, how much could it shrink before it would affect the relationship of the Earth and the moon and the tides and the gravitational pulls and tugs?
That's an excellent question. The fact is that even though the moon is shrinking by a small amount, by every measure that we have right now from the population of these small faults, it isn't changing the mass. So it's only changing the diameter of the moon by a small amount, and that will continue to be the case again over the next probably billions of years as that outer liquid core continues to cool down. But the mass of the moon will not change, so it really shouldn't affect the tides. What is really going to be the bigger effect is the fact that the moon is receding away from the Earth, is that Earth-moon distance is not constant. And it's those tidal forces that are coming from not only the Earth creating tides on the physical tides on the moon, but the moon trying to slowly recede away that will have that kind of an effect on Earth's tides.
I think it does that by about a centimeter or so a year.
It's very slow. Yeah, it's about 3.8 centimeters a year that the moon is getting further away from the Earth.
Okay. We have another question from an online viewer. How does the camera on LRO compare to my phone camera?
Wow, that's a great question. In fact, it depends on which camera we're talking about. The wide-angle camera is kind of more like the charge couple device that's in your cell phone. So they're very similar. The narrow-angle camera, those two telescopic cameras are very different. They are literally like line scanners. They scan only a strip of the moon at a time, and it's literally the motion of the orbit that allows us to build up the image. And that's mostly because, again, of the very, very high resolution and the actually fairly low orbit that we're in around the moon. Right now, the Lunar Reconnaissance Orbiter only gets probably about 150 kilometers away from the moon at its maximum.
We have another question from the audience.
How is the data sent from the LRO Earth, and what are the biggest challenges with sending the data back to Earth?
I'm sorry, the first question was how
is
far
the data sent back to Earth?
Oh, how is the data sent back? Okay, this is also a great question, because when you're getting 440 gigabits of data a day, you've got to have a sort of special relationship, because most of the data that's returned, and Jim can explain this better than I can, all the data that's returned from any planetary mission is coming through a series of antennas that are distributed around the Earth called the Deep Space Network. And those allow us, again, during different times to communicate with, again, every spacecraft that we have operating in the solar system right now. We are very fortunate with LRO that we have a dedicated 70-meter antenna that is literally ours for the most part to collects that data. So it's the only way, literally, we could get that much data back.
Now that technology is going to change in the future, because currently that's done with radio waves, and there's only so much information you can bring down with a radio wave. The next big step is optical communication, where the wavelengths are much smaller, and now we can transfer much more information. So we're looking ahead in the future, developing a variety of techniques where we're going to go perhaps to Mars or out into places farther than the moon and send that data back in light, and we'll use a telescope to receive it.
All right, we have another question from an online viewer. How is LRO powered?
Also a very good question. We have, again, the advantage of being in lunar orbit, so you're only about 283 million miles away from the Earth, so you're really not that far away, and so we use solar panels. There are solar panels on the spacecraft that literally provide all the power it needs to operate.
All right, and a question from the audience now.
How's the Earth acting as a tidal force on the moon? Because the moon is facing the Earth always in the same way, so the other way around, the Earth rotates and then it sends ripple effects through the Earth, but with the moon that shouldn't be the case.
Well, okay, I think if I understand your question right, it's a great question, because most people think of, when they think of the effect the moon has on the Earth, they think of, again, obviously the tides. I mean, the tides rise and fall, and it's the moon, but it's also the sun. It's the interaction between the two. But many people don't realize that the Earth exerts solid body tides on the moon. So the moon doesn't have a body of water, but its crust is actually pulled a little bit. It's about, at maximum, about 30 centimeters or so. If it were a body of water, you know, so it's not going to be much. But it's enough that you literally build up stresses from that flexing motion, again, coming from the tidal interactions.
But there's not really any motion because the moon is always facing the Earth in the same direction, right? So it's
okay, yes, but it is, yes, but it's kind of like, again, it's kind of like that one diagram I showed where it's being pulled in one direction and then it's relaxed. And then it's pulled again, but you're right, it's always that, it's always the, what we call the sub-Earth point and the anti-sub-Earth point. It's all happening around that.
One of the ways to think about it is, of course, the closer these two objects are together, the stronger that tide is. The moon is in an elliptical orbit. It's not circular. So as it goes around, it actually is getting that tugs and pulls, that constant dissipation of that heat that has to go on. Then another thing happens. It actually is trying to turn on us like this. And that's called libration, and we can actually see a little more than half the moon from Earth. And that also is a tug and pull between the Earth and the moon that heat has to be dissipated too.
Yep.
All right, great, thanks. Another online question. If LRO is in orbit around Earth, what could we see? What would it show us about the Earth?
That's a really interesting question. I think that as powerful as the cameras are, especially the telescopic cameras on LRO, they are probably not as powerful as some of the cameras that are being flown on satellites that are looking at the Earth right now, that can probably see down to several centimeters as opposed to tens of centimeters.
You know, one of the really iconic images that was created by one of the Apollo astronauts as they were orbiting the moon was to watch the Earth rise above the moon. You know, the beautiful ocean world Earth, and it was a view that we never really thought of before, and it was so captivating. LRO sees that also and can make beautiful images of the Earth rising above the moon. The contrast is incredibly striking, okay? This is the blue marble, Carl Sagan called, the ocean world. And I really like what Buzz Aldrin said as he walked around on the surface of the moon. He really appreciated the vistas and how much different they were, and he called the moon a magnificent desolate. And so when you're in the museum upstairs and you walk around and you see the beautiful images, think about that contrast.
And we have another question from the audience.
Hi, my name is Anna Samuels, and I'm a student at Arizona State University with friends in ASU lunar thing. I have a question. So is there any possibility in the future after the LRO finishes in the moon, could it go to, say, Mars or a different planet to investigate? Pictures?
Okay, I can easily answer
Yes,
that.
I was going to let Jimmy answer that.
LRO will live out its life at the moon. It will eventually run out of fuel. And depending on its orbit, and there's only a few orientations of that orbit that actually are stable, it'll more than likely end up in an orbit for which the moon will eventually bring it down and it will crash. So that's the fate of LRO.
And we have another online question. Are the cameras on LRO black and white or color? And maybe you could also clarify the non-visible wavelengths that these cameras also see in.
Well, it's a very good question. Again, we have said between the two different cameras, the narrow angle camera and the wide angle camera, two different ways of looking at the moon. And the narrow angle cameras look strictly in are black and white. So those images are literally just one channel. We're sampling just one area of the visible spectrum to get those images. The wide angle camera, again, has a series of filters which sort of slice the visible spectrum up into sample areas that we then take those separate images to put together to create the color views of the moon. The channels that Matt was just talking about, we also see out a little bit outside of the visible spectrum into the UV, which is where the human eye is not sensitive. And again, that helps us to look at specific sort of characteristics, again, of the materials, particularly water.
You know, one of the great features about LRO is the ability for us to be able to combine the data from several instruments. And as you're up walking around in the gallery, you'll see some really beautifully, strikingly colored images, deep reds and deep blues. That actually is altitude data that comes from one of the other instruments called LOLA. This is the Lunar Laser Altimeter. And that is all about sending laser light down to the surface, having it reflect, coming back to the instrument, timing that. And if you're closer, the time is shorter. If you're further away, it's longer. And that information then gets translated into an altitude. And when you map that onto the LROC data, the LROC data, you see those beautiful highs and lows, the crater rims, the deep valleys, the basins, and you really get an appreciation of the variation in the altitude on the moon. And it's huge. The backside of the moon, there's that place called the South Pole Aitken Basin. It's a huge impact region. And so when you go up there and you look at it, it's very dark blue. That means it's very low. It's about 15 kilometers in depth, which if you go to the Earth, where can you find a place of that latitude or altitude difference? You have to go to the top of Mount Everest and the bottom of the Marianas Trench in the ocean to get anywhere near that variation in height. And yet, it's common on the backside of the moon.
All right, and we have an audience question.
Bob Ivers, I have a question about lunar dust. Now, without environmental erosion, is it created by impact pulverization?
Yeah, the dust is created by impacts over and over and over. And you take the silicate material that's there and you shatter it. And when you look at it, we brought it back, and when you look at it under the microscope, it's really spiky. And actually, when we found out about that, that actually can be a hazard to our astronauts walking around, because if that gets into the lungs, it can really tear up the alveoli and really cause some lung damage. So understanding the processes that create that regolith, understanding its composition, its distribution, and that's what, as I mentioned, the mini RF is all about on LRO.
Yeah, the moon is constantly, again, because it has no atmosphere, the moon is constantly being hit by some large objects, but it's also being hit by micrometeorites, almost, as I said, constantly. And that is its primary erosive power, is just this constant, relentless bombardment.
We're going to take one more online question. Will data from LROC help plan future landing sites for the moon?
Absolutely. And in fact, there's a number of space agencies that have asked us for high-resolution data. The Indian Space Agency now is planning a lunar lander. They need the kind of data that we have created, and they are considering several sites, and that data is available to them like it is everyone else in the United States because it's online. So this forms a really important resource for all these agencies to use.
Great. Well, thank you both for being here and sharing all of this information about LRO and the Lunar Reconnaissance Orbiter Camera. And thank you all for coming. Thank you to Boeing for the support. Welcome to the museum.